Hello everybody, and welcome back. In this video, we're going to be taking a look at the second last question, question number 24, on our 2019 Cayley contest. Roberta chooses an integer r from the set 2, 3, 4, 5, 6, 7, 8, 9, an integer s from the set 22, 33, 44, same thing but multiplied by 11, okay, and an integer t from the set 202, 303, 404. So again, the same all the way up to 909. Just we took each thing from the first set and multiplied it by 101, I guess. Okay. How many possible values are there for the product RST? Interesting. So they want the different values. So obviously they're not just saying, all right, you got 8 things to choose times 8 things to choose times 8 things to choose. 512. There's nowhere near that that number in our potential answers. But so I guess if I chose a 2 here, the 44 here, and the 808 here, I'll get 2 times 44 times 808, which will be, take out the factor of 2 and 11, you'll get 2 times 4 times 8. Or not 2 and 11, 11 and 101. And you'll get 64 times 11 times 101. Right? Okay, but if I had chosen the 8, the 22, and the 404, we'd have the same thing. Because take out the 2 from here, take out the 4 from here, you'll get 8 times 2 times 4. Again, 64 times 11 times 101. So we're always choosing one number from down here. So we'll always have a factor of 11. We're always choosing a number from here. We'll always have a 101. So it doesn't, those numbers don't really matter, I think. So we could probably write that down. We get factor of 11 from S and 101 from T, regardless of what we choose. So why not just think of it as pick R from 2, 3, 4, 5, 6, 7, 8, 9. Pick R from there. Pick S from, we'll take out the factor of 11, and it's just the 2, 3, 4, 5, 6, 7, 8, 9 again. And taking out the 101, you'll get 2, 3, 4. You see what I'm saying? The 11 and the 101 are guaranteed to come from any factor in these second sets, so just factor that out, because we're talking about a product here. So really what we've got is we're choosing 3 numbers from 2, 3, 4, 5, 6, 7, 8, 9, and we're asking where are the unique products there? What are the unique products? Picking 3 times out of 2, 3, 4, 5, 6, 7, 8, 9. Just pick 3 times out of there. Okay. So, what can we do there? Well, I suppose, so we're really just picking from that set, pick 3 times. Okay, so how do we keep track of the products? Because it doesn't matter the order we pick things in, and I think that there's lots of different ways to get the same product. So for example, choose 6, choose 7. That's the same as if I'd chosen 4 and 9 and 7, because 6 times 6 can be expressed as 4 times 9. So there's going to be a lot of overlap, and what we want to do is keep track of that. So now for any given number, there are lots of ways to write it as a product, but there is something unique. For any given number, there's a unique way to write it out as a product, and that's to look at prime factors. And maybe that's why there isn't 1. I mean, we start this set at 2, then 3, then 4, all the way up to 9. So there's no 1, so maybe they're trying to hint at prime factorization. If that's the case, let's instead write every number in its prime factorization. So if I picked 2, that brings 1, 2 to my prime factorization. 3 brings 1, 3. Now 4, picking a 4 means that at the end I'll have 2 2s. 5 is 1. Now 6 is kind of interesting because it's 2 to the 1, 3 to the 1. And it's the only one that is not just a prime or a power of a prime. So 6 is kind of interesting. Now, what could we do here? If I ignore 6, if we just ignore 6 for a moment, let's ignore 6. What can I do without 6? Because 6 is kind of an oddball. 6 is not a single power of a prime. So let's ignore 6. We won't forget 6. We'll bring him back a little later, but I just want to investigate just the powers of primes for a moment. Now, we can choose, we could choose powers of 2, powers of 3, powers of 5, powers of 7 with what's left over. But what possible things could we get? So if I just pick one power of 2, I'll get a factor out of my 3 picks. If I only pick one power of 2, I'll get 2 to the 1, or 2 to the 2, or 2 to the 3. So if I'm picking only one power of 2, that's 3 possibilities. But if I'm allowed to pick powers of 2 twice out of my 3 picks, I get a bit more. Maybe it's a good idea to keep track of that. So let's say we pick n of prime p the number of factors in, no, it's not p, let's say RST. And we'll keep track of the number of possibilities. So if I were to pick one power of 2, and that's all I'm allowed, I could have 2 to the 1, 2, or 3. That's 3 possibilities. If I pick 2 powers of 2, well, I could have I could pick the 2, I could pick 2 again. So at bare minimum, I could have 2 to the 2. At most, I could pick 8, and I could pick 8 a second time, and that would be 2 to the 3 plus 3, so 2 to the 6. And I can get just about any other combination in here. So actually, let's not write those. Let's say I could have 2 to the 3, 2 to the 4, 2 to the 5, or 2 to the 6. Right? If I want 2 to the 5, just pick 4 and 8. I don't care the order I pick, because in the end, we just care about what factors we've got. So 2, 3, 4, 5, 6, that's 5 different possibilities. So if I'm allowed to pick 2 powers of primes, and you can, 2 powers of 2, and you can see I'm getting sort of organized with my chart and my possibilities. I want to be able to make these numbers, and I want to be very precise. Now, if all 3 of my picks are powers of 2, at bare minimum, I could pick 2 to the 1 each time, and I could get 2 to the 1 times 2 to the 1 times 2, so 2 to the 3. At most, I could have each one be 8. 2 to the 3, and that would get me a product of 512, or 2 to the 9. And I'm pretty sure I can get every number in between. So that's 7 different possibilities. Now instead, what happens if I were picking just one power of 3? What could I have? Right? So now that I've got starting to get this list, suppose there's 3 ways to pick one power of 3. I know it's not, but now when I try to make my number, suppose I pick one power of 2, and then, or let's say 1 power of 3 and 2 powers of 2. What possible products could I get? Well, there's lots of different ones, but there's 5 different ways to pick 2 powers of 2, 3 different ways to pick 1 power of 3. That'd be 15 different numbers we'd get. Kind of nifty. Now, if I'm just picking 1, 3, I could have 3 to the 1 or 3 to the 2. So actually, it's 2 different possibilities. Right? If I pick 2 powers of 3 or 3 powers of 3, I can get 3 to the... At minimum, it's going to be 9 if I've got 2 powers of 3. Or I could have 27, or I could pick both of them be 9. I could get 81. So that's 3 possibilities. And if I had 3 powers of 3, they could all be 3, they could all be 9, or they could be anything in between. So that'd be 4 possibilities. Okay. And then there are powers of 5. I could pick 1 power of 5, but there's only 1 power of 5 available. So there's really only one way to do that. You'd get 5 to the 1. There's only one way to pick 2 powers of 5. Just pick both of them. There aren't different powers of 5 available. Same with 5 to the 3. So even if I picked 3 different powers of 5, I know which numbers I'm going to get. The exact same thing happens with powers of 7. So if I pick 3 powers of 7, there's only one way to do that. You've got to pick the 7s. Whereas if I'm picking 3 powers of 2, I could pick an 8, and then a 4, and then maybe another 8. There's more variation here. Okay. Now, so again, we've left 6 out, and this is actually kind of nice. I'm gonna keep leaving 6 out. So we'll see what we can do without 6, and then we'll bring 6 in and see what 6 might be necessary for. For example, without 6, there's no way to do 2 times 3 times 5 times 7 as part of RST. There simply are not enough different factors available. So there will be a need for 6 later on, I'm sure of it. How many times we'll need 6, I'm not entirely confident. Okay. But now, when it comes down to picking my numbers, there's some options. I could pick all 3 of R, S, and T, other than the 11 and the 101, which I've already said we can ignore. They have the same prime power. So either I'm picking all 3 powers of 2 or all 3 powers of 7 or whatever. So there's 7 different numbers that come from picking all powers of 2. There were, I think it was 4. Yeah, 4 for all powers of 3. If I'm picking 3 powers of 5 or 3 powers of 7, there's only one way to do that. That gives me 13 different products, and they will be different products. At the same time, you could have R, S, and T have all different prime powers. So this is me saying, all right, you're only going to get 1 power of 2, 1 power of 3, and 1 power of 7. Make your choices. But there's only so many choices. For example, the power of 7, there's only one way to do that. So if everyone has different, then we're saying something like, okay, there's 3 ways to pick your power of 2, 2 ways to pick your power of 3, so that's 6, and then 1 way to pick your power of 5. Multiply them all together, so 6 ways to do that. 6 ways to do, so this is 2, 3, 5, 2, 3, 7. We would need 2, 5, 7, which is 3 times 1 times 1, and 3, 5, 7, those being the different powers. And there were 2 ways to pick 1 power of 3. So that's 2, and that's 17. So in total, we already have 30 different products we could have, RST. Now, we're not up near the 80s or even 90 yet, but we're on our way, and I definitely know that these factors are different. Now, how many other ways can we pick powers of primes? Well, we could pick 2 of the same and 1 different. Okay? So we could pick 2 of the same and 1 different. Okay? So, for example, if I pick 2 powers of 2 and 1 power of 5, I'll list the second thing, the smaller one, the one that I'm only picking 1 of second. That would be, so 2 powers of 2, 5 ways to do that, 1 power of 5. So there's 5 ways to do that. What if I'm picking 2 and, I guess 3. So powers of 2, so 5 ways to do that, 1 power of 3, 2 ways to do that. So that'd be 10. 2 and 7 is going to be the same thing as 5, with 5, so 5 again. What if I had 3 and 2, or 3 and 5, or 3 and 7, or 2 powers of 5, 1 power of 2, 2 powers of 5, 1 power of 3, 2 powers of 5, 1 power of 7, or 7, 2, 7, 3, 7, 5. Now, there's only one way to do your powers of 7, your powers of 5, so no worries there. Now, if I had 2 powers of 3, so something like 3 squared, and we could match that up with 1 power of 2, so like 2 squared. There'd be 9 ways to do that. I'm having a thought here for a moment. 9 ways to do that. The powers of this, so there's 3 ways to pick 2 powers of 3, 1 way to pick 2 powers of 5. What was it? 1 way to pick powers of 2. Or sorry, 1 way to pick powers of 5, 3 ways to pick 1 power of 2. Now, I just had a thought here that this question might not be as easy as it's currently turning out to be. Because this is a lot of numbers. This might be close enough to get to 80. But now I'm worried that there's some overlap. Because 2 squared and 3 squared could be, I pick a 2, I pick a 2, and I pick 9. Or it could be, I pick a 4, and I pick a 3, and I pick a 3. So that's another way to do it. So maybe this isn't the best way to break it down. Now, I'm not going to run into that trouble with these cases. But I could run into it in this way. There might be some overlap. There might be some numbers that can be written as 2 powers of 2 times 1 power of 3, and 2 powers of 3 and 1 power of 2, if you got something like that. Can we get the same problem elsewhere? I don't think so. Not with 3s and 7s. Because there's only one way to pick your power. So if I say, for example, I'm picking 2 powers of 5, I know I'm going to have a 25. There's no way to get 25 other ways. But the fact is, the 9 could split into 2 3s. The 4 could split into 2 2s. And so there's different ways to do that. So let's take a closer look at the 3s and the 2s, because it looks like there's some possibility of overlap. So what's the problem? The problem is I can get the same number by using 2 2s that I can just by using 1 2. So there's overlap there. And I can get the same number using 2 3s that I can with 1 3. So it looks like 2 times 1 different. It looks like there's 2 overlaps. The other one being 2 to the 3 times 3 squared could be, I pick a 4, I pick a 2, and I pick 9. Or I pick 8, 3, and 3. So I'm going to have to subtract 2 for the overlap. But we don't get any overlap over here with the 5s or the 7s or anything like that. It's the fact that, now, you might say, oh, but, you can get 3 over here as well. But if I'm picking 3 2s, I'm not also picking some 3s. It's the fact, it's only going to cause a problem between 1s and 2s. So yes, we can get 5 in 2 different ways using powers of 3, but if you're using 3 powers of 2, you're not also using you're not using any other powers of 3. So there's not this sort of wiggle room. Okay, anyway, so 13, 17. I'm just going to keep my calculator out. So 5 and 10 and 5 and 9 and 3 and 3 and 3 and 2 and 1 and 3 and 2 and 1 is 47 minus the 2 for overlap, and we get 45 possibilities. So far we're at 75 possibilities. 75 different products, and it's important that we catch this minus 2 here. Well, actually, let's keep track of that. Maybe it's not important that we catch that. We get that minus 2 in there, because maybe the answer we get by leaving it in there isn't possible. Maybe we will get maybe we'll get 90 as our answer, and if we'd left that in, that'd be 92, and that would be sort of a signal to us to go back and look for something else. Interesting. Okay, now, so all 3 factors different, all 3 primes the same, 2 primes of one type, 1 prime of another type. That's the only way we can put things together this way. But that's still just 75 things, and 75, we're not in the 80s yet. We're getting close. But what have we missed? Well, we've missed 6. And we haven't used 6 yet, so let's bring 6 back in the mix. So now let's consider numbers that have to use 6. Okay. Now the first question I'm going to ask, like, how many 6s do we need? Because we get different possibilities when we have 1 2 versus 2 2s versus 3 powers of 2. How many 6s do we need? Okay. Well, could I ever need 2 6s? 2 6s in something? Well, no, because 6 can be... Instead, I could have picked a 4 and a 9 in something. Okay? So you never need 2 6s. Anytime you have 2 6s, you could just do a 4 and a 9, and you'd get the same thing. Right? Similarly, you never need 3 6s, because, again, you could replace 2 of those 6s with 4 and a 9. Okay? So, if we're going to use a 6, if we need a 6, we'll have at most 1 6. And I've already said there's at least one case, 2 times 3 times 5 times 7, 6 times 5 times 7, that would have to use a 6 because there's no other way to get 4 different prime factors using what we've already done. So, it's 6 times something times something. We know 5 and 7 work, but what else could work? Could we have 6 times a 2? Well, no, because you wouldn't need the 6 there. You could do the same thing with a 3 times a 4 times whatever this... well, let's not use x. Let's call it a. Okay, so you wouldn't need the 6. I'm specifically saying I did all that other work. Now, we've left 6 out. What did I need 6 for? What can't be done without 6? And it turns out if I've got a 2 in my product, I don't need the 6, because I could have just gotten by with a 3 and a 4. So no 2's allowed. No 6's allowed, along with your 6. We've already said that. What if I had 6 times 3 times a? Well, that'd be 18. I can replace 18 with 2 times 9. So I don't... No 3's allowed. So no 2's, no 3's. What if I had 4? So that'd be 24... we can do 3 and 8. So I can't have any 4's. But if I got 6 and 5 and a, there's no way to rewrite 6 and 5 using anything other than a 6. Because it's got to have a factor of 5, which means you got to have the 5, so you got to have the 6. Same thing with the 6 and the 7. Those are good. What about 6 and 8? So that would be 48. Can I express 48 using any 2 of the others? Right? So 9's off the list, same with 7, same with 5. While 2, 3, and 4 are factors, way too small. So no, it's got to be 6 and 8, so 8 is allowed. 6 and 9 would be 54. And yeah, again, the things that are allowed are too small to have another digit. Right? So if I'm going to have a 6, I'm allowed to have 5s, I'm allowed to have 7s, I'm allowed to have 8s, I'm allowed to have 9s. Okay? So that's not that many. So what if I had 6, 5, and 5? Or 6, 5, and 7? Or 6, 5, and 8? And we can work each of these out. It'll have to be a different product, because there's no way to rewrite it without the 6. So it's just a question of, are these all sort of unique amongst themselves, or is there any overlap? Maybe, again, with the 8s and 9s, because powers of 2 and powers of 3 seem to be causing me problems. What else could we have? 8 and 8, 8 and 9, or 9 and 9. So let's just quickly grab our calculators and work them out. So 25 times 6, 150. 30 times 7, 210. 40 times 6 is 240. We're just looking for anything that is out of the ordinary or any overlaps. If this one out here works out to be 270, we've got another overlap and we need to account for that. Out of these 10 possibilities, what is allowed, what is not allowed? So 6 times 49, 294. 6 times 7 times 8, 336. 6 times 7 times 9. 378. Nothing different so far. I wasn't expecting that to happen because of the 7s and the 5s. But over here, something weird might happen. 6 times 8 times 8. 384. 6 times 8 times 9. 432. Again, not on the list. And 6 times 9 times 9 is going to be much bigger. 6 times 81 is 486. So it looks like they're all different. And these are the products you would get. You know, obviously some of these with 11s and 101s, but again, we ignore that. So you get 10 different possibilities here. And they're all different, and they all require 6. There's no other way to make it. And you'll notice that my 6, 5, and 7 is here, along with several others. Okay, but you have to have 2 powers of 7 here, so you can't just pick a power of 2 and a power of 3. You have to get 6 there. All right, so in total, what have we got so far? We had 13, 17, 45 is almost 47, with but we subtracted 2 for the overlap. We should maybe go back and double check that. And then 10, so that's 30, 75, 10, 85. 85 I'm currently saying is the answer. Is that a possibility? There it is. It's 85. If I hadn't caught that I needed to subtract, I would have thought the answer was 87. Fortunately, that's not there. So we would have said, oops, we goofed, and we would have gone back to double check. Now, 84 is nearby, so maybe we want to do another double check to see if there's any overlap. But really, the only place it could have happened is if you had 2 3s and 1 2 being expressed the same way as 2 2s and 1 3. And we've kind of got that sorted out. And that was the only way it could happen. It couldn't have happened with 2 3s and a 5, for example. But let's just do a quick double check, make sure there isn't anything missing. And we've got 2 is on both lists, 3 is on both lists, and that's it. 2 is the only one on the list down here. So I'm satisfied that 85 is the answer. Now, I don't know whether or not this ignores 6 and work with powers of prime and prime factorization is necessarily the best way to do the question. You might be able to do some combinatorics, maybe with some sort of inclusion-exclusion thing. We're seeing a little bit of that here. But I would say it's not that bad. I mean, right from the start, they're asking us for the different possible products, RST, right? And so, immediately you ignore the 11 and the 101, obviously. And then, well, if you're looking for unique products, you can't just write them out with any old numbers because, as we've seen, there's lots of ways to rearrange things. So I think unique prime factorization is the best way to go. And then you ignore 6, and then you say, well, how many factors of 2 could I have? And then what possibilities do we get there? So I think it's very nice. And then we brought 6 back in the end, and everything worked out with 6. So I'm saying it's a good question, a little long, but that's okay. If you have another way to approach this question, a better way to approach it, I would absolutely love to read about it down in the comments below. So, please let me know. I'm always eager to learn other ways to do questions. But I think that's it for 24. Up next, we're going to take a look at Cayley question 25 and sort of close off the whole paper. So until then, have a wonderful day.